Hello, this is my video for Lab 1, Constant Velocity, and I am Xiaowei Shi. The purpose of this lab is to compare the position of a real-life object moving at constant velocity with that of a computational model of that same object moving at constant velocity. This lab is also to help us understand the principles of Newton's second law. Some important equations to remember for this lab is Newton's second law, which states that force is equal to mass times acceleration, and the velocity update formula, which states that final velocity is equal to initial velocity plus the net force divided by mass times the change in time, and the position update formula, which states that final position is equal to initial position plus the average velocity times the change in time. To begin my lab, I first have to choose a system, which was a marker, and the surrounding, which was everything else. To track the position of my marker as it moved across the table, I used tracker, which was the actual position of the marker. And then to track the predicted position of the marker through data I obtained from tracker, I used GlowScript. My hypothesis for this lab is that in my computational model, there will be a constant velocity due to the fact that there is no net force, as we don't consider for friction and drag. And because there is no net force, according to Newton's second law, there will be no acceleration, thus the velocity will be constant. In my real-life model, there will be a negative net force due to drag force and friction, which results in a negative acceleration, causing the velocity to decrease. The initial conditions for my models are the initial position being negative 1.8296 times 10 to the negative 400 meters, the final position being negative 0.35400 meters, and the time interval being 0.802 seconds, and the average velocity calculated with the average velocity formula being final position minus initial position divided by time, which was negative 0.4414 meters per second. On this side, I'll be discussing my tracker video and my tracker data. On the left, each red dot signifies a position of the marker as it moved across the table. Each marker was taken approximately 0.033 seconds next to each other, as the video was taken in 30 frames per second. On the right, the table is my position versus time table, and that is where I received my initial position as well as my final position, as well as my time interval. On this slide, I'll be discussing my code and what I added and changed the initial code to match my data. First, I added the position update formula as to update my position after each timestamp. I did not add the net force as net force would be 0, thus it is unnecessary to add it to my code. Thus, the velocity update formula is also unnecessary, as due to the Newton's second law, since there is a net force of 0, there is no acceleration, thus velocity will not change. I added the initial position, which I found in my tracker, and I added the initial velocity, which is the average velocity that I calculated using the data from my tracker video. Delta D is 1 divided by 30, as the tracker video was taken in 30 frames per second, and the time interval, which I found in my tracker video, is 0.802 seconds. And here's the result. On the left is a position versus time graph using the data from the tracker video, and on the right is the position versus time graph generated by GlowScript. The speed calculated through the best fit line of the tracker graph was 0.443, which is greater than the speed of the average velocity, which would disprove my hypothesis. However, this could be due to the fact that my data was collected over a short time frame of 0.802 seconds. Thus, friction and drag may not have enough time to affect the velocity yet. And also due to the fact that there was an initial pushing force caused by my hands as I pushed the marker, which resulted in a slight acceleration. Lastly, I'll be answering the what if and what does it mean questions. If the axes were flipped, then the only thing that would be changed would be the signs for position, velocity, and force. Due to the fact that in my data, the marker was traveling in the negative x direction, if the axes were flipped, then the new marker would be traveling in a positive x direction. Thus, it will also have a positive velocity instead of a negative velocity. The net forces that equal to 0 in my model are possibly gravity, normal force, pushing force, drag force, and friction. In the y direction, there will be a gravitational force going down, and then a normal force going up, which equal out to 0 in the y direction. And in the x direction, there'll be an initial pushing force caused by my hand that pushes the object across the table, as well as an opposing drag force and friction opposing the movement of my object.